Hi everyone. This is the second video in the video lecture series discussing the definition of metric spaces. As I already told you in the first video, the only prerequisites required are definition of sets and functions, which you learn in your school. And if you know those definitions, and even if you're a school student, if you have an open mind to learn, you can follow this lecture series. In the first video, we talked about definition and meaning of metric spaces. We talked about where this idea of metric spaces came from. And if you haven't watched that video, I would strongly recommend you to pause right now. Use the link given in the description. Watch the first video before you proceed with this. If you have already watched it, don't worry, we'll quickly review it along with some extra information before we proceed with this particular session. In this session, we'll be discussing a few simple examples, and using those examples, we'll make some observations on the definition we are learning here. And these simple examples are basic examples which you may already know. These are not the only examples we'll discuss during the course of this lecture series. We'll be discussing more examples and counterexamples as we do challenges, questions from other sources, and towards the end there'll be one video discussing advanced examples which will help us understand about this definition further. So for now, we are going to be satisfied with simple examples because our aim is to get a basic understanding of this definition before we head to challenges. Let's quickly recall the definition of metric spaces. As I already told you in this definition, to start with the definition, we need a set M, which the only condition on it is that it should be non-empty, and we'll need a function rho which we will call a metric for M if it has domain M cross M and range contained in cross interval 0, infinity. Not just that, it should satisfy these four given conditions. Note that whenever I ask my students for definition of metric spaces, often they would quickly quote the four numbered condition and they will ignore the other parts of the definition. I would like to emphasize on the fact that all conditions on domain, on range, the conditions given in the last line here, that rho is a metric for M, ordered pair, everything is equally important. So let me give you a visual cue to learn this definition and to memorize this definition better. Imagine going for the name metric or the title metric is something like a prize given in a competition, and the competition has two parts. First part is there's a competition for function for sure. Two, when you go for the competition, you have to do the qualifier test, which will be done by the watchman. The watchman will ask you, is your domain M cross M? And then he would ask you, is your range contained in closed interval 0, infinity? If it is, the gatekeeper would open the gates for you. And then you have to run a hurdle race where you have to cross four hurdles. First hurdle is that rho of x comma x is equal to 0 for all x belongs to M. Second hurdle is rho of x comma y is greater than 0 for all xy belongs to M when x is not equal to y. These two are just simply talking about how the function can take only non-negative values, that is positive or 0, and when can it take 0, that is it can take 0 if and only if x is equal to y, and this should be true for all x and y belonging to M. The third condition, we talked about how it is talking about flipping the input will not change the value of this function. We talked about how it has something to do with symmetry in the previous video. And then the fourth condition, mysteriously called triangle inequality. We saw why it is called triangle inequality. We read it in a slightly different way in the previous video as the distance between x and y is shorter than the distance you travel when you go from x to y but taking a detour to z. That is going from x to z and then from z to y. Now, if the particular function, passes the test by the gatekeeper, and then he crosses these four hurdles, then this particular function is called a metric on M. Now, notice one fact emphasized here: rho is a metric for M. It is particular to M. And notice how we have emphasized the fact that this entire definition, the function rho, depends on the fact on this particular set M. The domain should be M cross M, and then the conditions here should be true for all x, y, and z belonging to M. So this particular rho has done this race for this particular set M, and hence it's a metric for M. And the ordered pair M comma rho is called a metric space. Let me emphasize on the fact that the ordered pair M comma rho is called a metric space. Now, sometimes, since writing this is a hectic task, we would simply say M is a metric space. To simplify our notation, when we say M is a metric space, what we essentially mean is M is a set which has a metric defined on it. We don't know what that set is, what that metric is, unless it's explicitly specified, but generally we'll just consider that M has a function rho which satisfies these conditions here. Now, let me make another observation. This particular definition was taken from Richard R. Goldberg's methods of real analysis. This may be a little different from what you learned. You may have used Bartlett and Sherberg, you may have used some other textbook for real analysis to learn this definition. So this may be slightly different from what you learned, but I leave it as a challenge for you to verify how all these definitions are essentially the same, no matter how different they are quoted in different books. One another thing you should notice is that we have excluded the possibility for M to be empty set here. That's because if M is empty, our study is trivial because there's nothing in it to measure distance between. So this is trivial. Maybe that's why the author openly just rejected empty sets from having a metric associated with it. So even if the definition is different from what you learned, you can verify how they all essentially mean the same and how they all essentially talk about the same concept in mathematics. We didn't do just that in the previous video. We talked about where this definition came from. We saw how the idea of distances is exactly the same as the idea of metric. We claimed that the idea of metric is nothing but rewriting the idea of distances in mathematical language. And that process of rewriting something from nature in mathematical language, we called it abstraction. I talked about how abstraction is the heartbeat of mathematics. So I talked about how, as a mathematician, as a budding mathematician, you should develop the skills to abstract ideas, to frame ideas into and rewrite them in mathematical terms. So we also talked about how you should be able to ask the right questions to the definition to understand it better, how we should be able to ask the right questions to the intuitive idea in your mind so that you understand the intuitive idea in your mind better and you'll be able to formalize it into words. That is, write down your intuitive idea into mathematical terms and frame it into a definition or a theorem or whatever it is. That was a quick recap of whatever we learned in the previous session. Let's quickly go ahead and see what we have to discuss in this video. Let's take a look at a few examples. And as I already told you, you're already familiar with these ideas because when I ask you for the distance between 3 and 6, you would be quick to say 3. But we know that 3 minus 6 is minus 3. But intuitively, you knew that distance between 3 and 6 is 3, even though 3 minus 6 is minus 3. That's because here, When we talk about distance, we are talking about metric, and that particular metric, we haven't qualified him to be a metric yet, but let's look at that particular function we are talking about here. The set of all real numbers is fancily written by mathematicians like this. And when I talk about set of all real numbers, I'll be writing it this way. Now I'm going to talk about a function rho which has the domain R cross R, codomain R. And the function is defined by rho of x comma y is equal to absolute value of x minus y. This is, and I'm going to claim that this particular function wants to go for the race we are talking about. It wants to win the title of metric for R. R is the set of all real numbers. So let's see. When he went for qualifier, the gatekeeper asked him the obvious two questions. One, what's your domain? And domain is R cross R, and problem solved. Two, but the codomain is R, right? It's not closed interval 0 comma infinity. Notice how the definition was worded. The definition said range should be contained in closed interval 0 comma infinity. Let's see if the range is contained in closed interval 0 comma infinity. Let's take any x belongs to R, that is any real number. Taking absolute value of that number, we know that that value will always be greater than or equal to 0. That is, this particular function, absolute value of x minus y, will always be greater than or equal to 0 for all x and y belongs to R. Hence, the range of this function is going to be definitely, range of this function rho is going to be definitely contained in closed interval 0 comma infinity. Please note that in fact, if you are a mathematician or if you have basic knowledge in functions, you can easily verify that the range will be exactly closed interval 0 comma infinity. It need not be strictly contained in it's exactly closed interval 0 comma infinity. I leave that as an exercise for you. So the gatekeeper is happy, he lets you into the race. Now we have to verify our 4 hurdles. We have to see whether this function can cross the 4 hurdles. First hurdle is 0 of x comma x for any x belongs to R. We know that absolute value of x minus x is equal to 0, hence true. Now second condition, again we know that when x is not equal to y, x minus y will not be equal to 0. It will be either negative or positive number, and we know that absolute value of negative or positive number will always be greater than 0. Hence, second condition is also done and dusted. To prove the third condition, we'll use a small property of absolute value, which you are already familiar with and you might have taken it for granted so far. Absolute value of xy is equal to absolute value of x into absolute value of y. Now, we are going to use this particular property of absolute value to proceed with the third condition. Rho of x comma y is equal to absolute value of x minus y, and then I am going to take a minus out in common out of it to get absolute value of minus of y minus x. Now why did I take the minus out? We know that what we have to prove is rho of x comma y is equal to rho of y comma x. We know that rho of x comma y looks like this and rho of y comma x looks like this. Now when proving something, sometimes you can take a hint from where we are heading to. We need y minus x. How do you make x minus y, y minus x? To do that, we can take a minus out simply. And that's what I have done here. Now, I'll use this property to simply say, simply split and take the absolute value of minus 1 out, which is nothing but 1, and your proof is done. What I'm talking about is when you're trying to prove something, sometimes you can take a hint from the final result that you have to reach and start constructing from the beginning using that hint. That's a very valuable tool you would come across in the future when you start writing definitions or when you start writing proofs. Let's take a look at the fourth condition. To prove the fourth condition, that is the triangle inequality, we need something, so a property, an inequality regarding absolute value given by absolute value of x plus y is less than or equal to absolute value of x plus absolute value of y. I'm not going to prove it. I'll leave it to you to research further into how it is true. And you can try prove it yourself. Now, that's the first condition, first thing we'll use. And second thing is a magical tool that you will use throughout real analysis, study of real analysis. That magical tool may sound trivial to you. For any x belongs to, say, let's restrict ourselves to R. For any x belongs to R, I'm going to add 0. And the 0, I'm going to rewrite it as minus z plus z for some z belongs to R. Here, adding and subtracting the same number essentially has the same effect as adding 0. But sometimes rewriting like this can help us simplify our proof. For example, in this fourth condition here, rho of x comma y is equal to absolute value of x minus y. Now we will add a 0 in between and we will use the inequality to split it. Now we have proved that rho of x comma y is less than or equal to rho of x comma z plus rho of z comma y, which is exactly what we want to prove. Turns out the particular function we were considering has convinced the gatekeeper to let him in, has crossed all 4 hurdles, and he has proved himself worthy of the title metric for R. And this particular function rho is called absolute value metric because we are making use of the idea of absolute value, or Euclidean metric on R, or simply, since there is the intuitive idea of distance that we have in our mind, we will call it the usual metric on R. Not the name, this name of Euclidean metric. Please remember that name because we'll be talking about it in detail. Euclidean metric is a word which is very interesting and we'll talk about it in detail in one of the future videos. Now, I'm going to leave this as a quick exercise. Instead of R, I'm going to consider the subset of R closed interval 0, 1. And I'm going to redefine a new function rho from closed interval 0, 1 closed interval 0, 1 to R given by defined the same as absolute value metric. Now I'm going to leave it as an exercise for you to prove that this will in fact be a metric on. This will in fact be a metric on closed interval 0, 1. I'll be quoting this in one of the properties we are going to observe later. If you want, you can pause the video right now and go ahead, finish it and get back here. Now let's talk about magic. You know that in Harry Potter there is a certain kind of skill that everyone is taught to imagine a place and to be in the same place, to travel to any place in the world by just imagining that place in their mind. That in the real world is called teleportation. Can you imagine what would happen if teleportation was possible in real world? The physicists have been trying to do it for a long time. They've been trying to make machines where you can teleport from anywhere to anywhere in a few seconds, in say 1 unit of distance. Here the distance may not be measure of length, it may be a second, it may be a nanosecond, we don't know what it is yet. They've been doing it for hundreds of years now, but they haven't succeeded yet. But what we mathematicians did, we set the math in such a world ready. We did the homework already so that when the physicists are ready with it, they can always trust on math to have shown them how that world will look like. Let's see how. Now imagine a world where It's a real world with real numbers, and there's a function d, I'm not calling it a metric yet, which has domain r cross r and codomain set 0, 1. And it's defined by d of x comma y is equal to 0 when x is equal to y, 1 when x is not equal to y. Here, notice that the domain is r cross r and the range is set 0, 1, which is a subset of closed interval 0, infinity. Hence, no issues. This guy enters the race with the consent of the gatekeeper. But he has to cross 4 hurdles. But the first 3 hurdles are easy for this particular function. And I'm going to leave it to you, because when x is equal to y, this is equal to 0, because that's how we defined it. When x is not equal to y, this is equal to 1, greater than 0. That's how we defined it. We know that when x and y are flipped, here this definition doesn't change. So the third condition is also easy satisfied. But the fourth condition requires a bit of machinery, but that's also easy to prove. So to prove triangle inequality, you need to consider 2 subcases. First subcase is when x is equal to y. Then we know that d of x comma y will be equal to 0 by the definition here. And we know one more thing. The RHS is d of x comma z plus d of z comma y. We know that this number is going to be either 0 or 1, and this number is going to be either 0 or 1. We don't know what these numbers are, but we are sure that this will be, RHS will definitely have either 0 or 2 or 1. These are the only possible values in RHS, and definitely this will be greater than 0, greater than or equal to 0. So first case, when x is equal to y, turns out our condition is satisfied. In the second case, when x is not equal to y, what happens is d of x comma y should be equal to 1. Now we'll have to consider 3 subcases. First subcase is that x is equal to z. When x is equal to z, z cannot be equal to y because x is not equal to y. Hence, d of x comma y, let me quickly draw a table to explain it easier. D of x comma y, d of x comma z, d of z comma y. Now when x is equal to z, let me call that condition subcase a, 2a. In subcase 2a, you have x comma d of x comma y as 1, that's sure, and d of x comma z will be equal to 0 since x is equal to z. D of x comma z comma y will be equal to 1 since z is not equal to y, and clearly is less than or equal to 1 is less than or equal to 0 plus 1. And let's consider subcase 2b. And in subcase 2b, again, d of x comma y is 1 and d of x comma z is 1 because y is equal to z, x is not equal to y, and z is not equal to y. Since y is equal to z, you have 0, and again, condition triangle inequality satisfied. Let's consider subcase 2c. And in subcase 2c, d of x comma y is equal to 1, and I'm going to put less than or equal to trivially because d of x is not equal to z, hence d of x comma z is equal to 1, z is not equal to y, hence d of z is equal to d of z comma y is equal to 1. So turns out in all the possible subcases and cases we have exhausted, we have shown that the triangle inequality holds true. So this guy crosses a race and proves himself worthy to be called a metric on the set R. Very interesting. And this metric is called discrete metric. And as I told you, if teleportation is possible, it will be 1 unit of distance between any 2 places in the world. In such a world, this is how distance will look like. We mathematicians further expanded the study to see how continuous functions will look like. We'll talk about continuity in future. how open sets will look like in this particular metric, in this particular world with discrete metric, if distance was like this. And we have found very interesting properties of this world already, even before the physicist could achieve it. So this is a metric on R, and this metric is called the discrete metric on R. Very interesting metric. We'll come across it again in future. Note that so far we have done 3 examples. What can be observed out of just simply 3 examples, right? Usually, to make any study, the people from other field like commerce and physics would take millions of data before they make any result. But in mathematics, it's so precise that even these 3 examples can give you valuable insights. These may be a bit trivial insight, but the reason I'm quoting them is, as I told you, I'm going to train you to think like a mathematician. Usually when we are learning mathematics, what we would do is we'll quickly read the definition which is given there, and we'll quickly try to see the theorems which follows it. And in the textbook, it will be given in a sequential order, so it's easy to follow and understand. But we often should try ourselves to think like a mathematician. That is, if we get a definition, you should be able to frame theorems or to observe properties of it. Try to frame it into theorems. Try to write it down yourself as a proof. That's a wonderful skill that each mathematician should develop, but unfortunately not so much emphasized in our classrooms these days. So by observing these facts out of these examples, what I am trying to do is to train you to think. Now, these are not the only observations you can make out of these, simply these three examples. If you have any more observations, please leave it in the comment below. First observation. We know that rho of x comma y is equal to absolute value of x minus y, or the absolute metric, and d of x comma y is equal to 0 or 1 when x is equal to y, x is not equal to y, which is also called discrete metric, are 2 metrics defined on R. Or in other words, the same set can have more than one metric. Let me quote it in a more fancier way. It is not mandatory that a set has a unique metric associated with it. A set may have different metrics associated with it. In fact, on R, you can define uncountably many metrics on R. I'll leave that as a challenge to you. How can you find more metrics on R which are not exactly these 2 metrics given on screen? If you find any, leave it in the comment. Let's make another observation. The absolute value metric we talked about, we claim that it works on R, and I left an exercise, but I said it also works on closed interval 0, 1. So turns out the same metric works on different sets. So it is not mandatory that a metric is unique to one set. So it may work on more than one set. Let me emphasize on that again. I said it may. I am emphasizing on the word it may. It need not work on every set. It may work on more than one set. So keep that in mind. We will talk about why I said may when we discuss advanced examples and counterexamples. Third observation. Consider the set here. Absurdity, right? It's not even numbers. I'm learning mathematics. Why should I consider such a set? Set has a smiley and a sad face. Turns out you can define a function on that particular set, and that function, in fact, you can go ahead to prove that this will be a metric on the set M defined here. This particular metric, you can eventually prove that this is nothing but the same idea of discrete metric we defined earlier. But the fact we are going to observe here in this third observation is that it need not be a set of numbers for it to be for us to define a metric on it. Given any non-empty set, we can find a metric on it. And in fact, that leads me to my fourth observation. Discrete metric, turns out it works on any given set. It worked on the set of all real numbers. It worked on a totally absurd set that we picked. Pick any non-empty set, turns out discrete metric works on it. As I already told you, there is something curious about this metric. We'll explore it further in one of the future sessions. To conclude our discussion, in the first video we talked about the definition of metric spaces and about the word of abstraction, how we abstracted the idea of metric from the real world natural idea of distances. In this second video, we discussed two simple examples, absolute value metric and discrete metric on R, and we talked about how absolute value metric also works on closed interval 0, 1. Then we made a couple of observations, 4 observations to be precise. One set may have different metrics. Same metric may work on different sets. We can find a metric on any given non-empty set, and then we talked about how discrete metric works on any given set. I also would leave it as an open question if you can make any more observations out of these 3 examples that we discussed so far. I'm promising you there are many more observations that you can make. Please leave it in the comment below. And learn to enjoy the process of learning math. Learn to enjoy the process of learning math as imagine you are going to a forest. You are a very adventurous person. You're going to a forest. Either you can take a guide about what all to do. How do you take a step? How do you look around? Or you can just walk in and enjoy, have an adventurous trip, where you try to observe things around. You try to see an elephant in real. Obviously, you have to take precautionary measures, but you try to see an elephant in real and try to see what an elephant is with your own eyes instead of just reading it from a book. You can imagine math exploration and math learning that way. You're going on an adventurous trip where you're exploring the subject in detail. You're exploring it. You see something new. You try to see its property. You try to define its property. You try to see what happens when you do something else with it. And that's why learning mathematics is so much fun. And I believe I'll conclude the session with this for now. In the future, in the next video, we'll be talking about a couple of examples and counterexamples of metric spaces. Counterexamples of metric spaces. And I thank you for watching this video. Stay tuned for more study materials, quizzes, live classes from this channel. Please like the video if you found it useful. Subscribe to the channel for updates about future classes and materials that we produce. Please don't hesitate to visit mathematicos.in. The link will be given in the info box on top, somewhere around here maybe, and you can use this fancy button here to subscribe to the video, subscribe to the channel. So thank you again. I'll get back to you soon with more materials.